Welcome back to AP Chemistry with Mrs. Mays. We're in acid-base equilibrium, and today we're going to talk about how to prepare a buffer solution. So here's our example. An environmental chemist needs a carbonate buffer of pH 10 to study the effects of acid rain on limestone-rich soils. How many grams of sodium carbonate must she add to the 1.5 liters of freshly prepared 0.2 molar sodium bicarbonate in order to make the buffer? The Ka of sodium of the bicarbonate ion is 4.7 times 10 to the negative 11. So we have all the information we need to prepare our buffer. Let's see how to handle the mathematics. So I moved this into notebooks so that we'd have more space to solve this type of a problem. Let's start with the Henderson-Hasselbalch equation. The pH is equal to the pKa plus the log of the base over the acid. So we put the concentration of your conjugate base over the concentration of your weak acid. Let's look at the equation that we're working with. The equilibrium we have at play is between hydrogen carbonate or bicarbonate and the carbonate ion CO3 2+. 2 minus. You meant what I knew. So this is our acid and this is our conjugate base. And notice in our buffer problem, here's where the conjugate base will come from, and this is the salt that our weak acid comes from. So we have both of those in solution. That's how we know we're preparing a buffer. And we also know that we have 0.20 molar concentration already of the bicarbonate ion. So let's start using the Henderson-Hasselbalch equation. We know that we want a pH equal to 10. We also know how to take the pKa, that means the negative log of our Ka value, 4.7 times 10 to the minus 11 power. There's our pKa, plus the log of our conjugate base, which is the thing we're trying to solve for, right? So we're going to call that x over the log of our weak acid. Our concentration of weak acid is 0.20 molar. So now we have to do mathematics with logs, which is not the same as doing regular old math, right? Logs have their own rules. So first take the negative log of 4.7 times 10 to the minus 11. Let's be more specific. Okay, so negative log of the Ka gives us 10.3279, so we don't need that many sig figs. We'll call it 10.33. So then I can move that across to the other side by subtracting, so I get 10 minus 10.33 equals the log of x over 0.20. And when we're dividing logs, that means what we're doing here is taking the log of the carbonate concentration minus the log of the bicarbonate concentration. Because when we divide numbers with powers, we subtract the powers. So I end up with 10 minus a 0.33 gives me negative 10 minus 10.33. It gives us a negative 0.33. And what is the log of 0.2? Log of 0.2 is negative 0.6989, blah, blah, blah. Okay, so I'm going to add that back over here, 0.6989, all those digits. So combining our two values, so let's see. So I have a positive 3.71 equal to the log of x. So now we have to undo the log. So we take the anti-log. So I raise 10 to the power of 3.71 and 10 to the power of the log of x, where now this cancels and x will be equal to 10 raised to 3.71. So what is that? Anti-log 3.71 0.371 decimal places. Try again. Anti-log 0.371, and that gives us 2.34. That's much more reasonable. 2.349, so we'll call it 2.35 molar concentration for X, which is our concentration of the carbonate ion that we need in our solution. We haven't answered the question that was asked. We need to calculate how many grams of sodium carbonate must be added. So now it's a stoichiometry problem. I have 1.5 liters of solution, and I need a concentration of 2.35 molar. So that's 2.35 moles per liter. And for every 1 mole of carbonate ion that we need, then I'm going to require 1 mole of sodium carbonate. And that has a molar mass of somewhere around 106, right? 1 mole of sodium carbonate weighs 106.01 grams. So once we work all this out, I find that it's going to take 373.7 grams of sodium carbonate to add to my solution to create the buffer that will have a pH of 10. So let's look at some tips in producing buffers. So first tip to consider, you want to choose an appropriate acid-base pair. So we select a weak acid whose pKa is within plus or minus 1 pH unit from the desired pH of your buffer. So if you need a buffer of 4, then you need a pKa that is within either 5 or all the way down to 3, somewhere in that range. On the other hand, if you want a buffer in the range of 10, then you're looking for a weak acid whose pKa values range from 9 to 11. And that's how we would choose the right acid-base pair. Also remember that the composition of the buffer does not depend on the volume of the solution. As long as your ratio of your conjugate base to your weak acid stays the same, then you'll have the same pH in your buffer solution. And here's why that's true. Because changes in volume affect both the concentration of the acid and the concentration of your conjugate base at the same time. So they'll both be influenced by the same amount, so your ratio remains the same when the volume changes. So don't stress about, oh, now the volume's going to be more or less. It's the same ratio. Use Henderson-Hasselbalch and you'll get it every time. We'll see you guys in class.